Yeah. Today we'll discuss about the theory of computation. Coming to the content of this theory of computation, today we'll discuss introduction, basic terminology of theory of computation. Why we are going to use this theory of computation? Coming to the introduction, it says that the automata theory is a theoretical discipline of a computer science and mathematics that focuses on the logic of computing in a relation to basic mechanism known as a automata. So here we have the computer. Computer will takes the input and it will move into the another state. That is, it is going to be performing some task in a mathematical manner. So it is related to the theoretical study of the computer science and mathematics. So it gives the some automata machine. Here, automata is nothing but a machine. Here, the scientist may use the automata to study how the machines calculate the functions and solve the issues. The primary aim of creating the automata theory was to provide techniques for describing and analyzing the dynamic behavior of discrete systems. So here we are going to use the scientists will going to use the some formulas to calculate and gives the solution for the automata theory to perform some task. And it is going to be creating some dynamic behavior of the system. That means it is moving from one state to another state by reading some input. So we are saying that it is a dynamic behavior of the discrete system. The system contains some states. It will changes based on their input taken, and it is going to be computing some function and giving the solutions for the particular problem. A word automata which is closely linked to automation is where the term automata first appeared. So from this, we got the automata is the first word we create. They given the name. Coming to the basic terminology, that means what we need to convert the machine as an automata. What is that basic terminology we're going to use here? Here first we are going to use the symbol. Symbol is nothing but a small building block where which can be any alphabet, letter, or special characters. So here we're going to consider as the symbols. And next one is the alphabet. Alphabet is represented as a sigma. Alphabets are a set of symbols. It may be the set of alphabets, letters, or special characters, whatever it may be. But it is always a finite number. That means it has some value. It will be represented as summation equal to 0, comma 1. Here 0, comma 1 is represented as a binary value. Either it will be 0 or 1 as a input for the machine at one state. Sigma equal to 0, 1, 2, 3 up to 9 values. It will be the numbers. Sigma equal to ABC. We can consider the input values as ABC also. That is the alphabets. That is the letters we can say. Or we can consider as the alpha capital letters also. And a special characters like dollar, union, intersection, subsets. Like that, we're going to use the symbols in the alphabet for the reading the input value. All these are the different types of input values for the automata or a machine. Next, we have the string. String is a finite sequence of symbols from some alphabet. That means we're going to consider some alphabets. That is sequence of characters will give the string. The string is generally denoted as W. That is a word we can say that. So word contains the set of characters or letters. And the length of the string is denoted as mod W. The length will be defined as a mod W. A empty string is represented as epsilon. There is no characters in the string. Then we can represent as an epsilon. Here it is a here we have in the epsilon. This is called the epsilon. Sigma equal to a comma b. So here we consider that input symbols as a comma b. That means we consider a or b as an input for the automata. So the length of the string will becomes a 2. Here we have the input values AB. So it is a 2 characters. So the length will be the 2. And we have the formation of string. We can consider as AA, AB, BA, BB. So within the given input only, we are going to be forming the strings. We can form the string with the two length 2 AA or AB, BA or BB. So four ways we can represent the strings. So number of strings equal to 4. That is, this is a 1, 2, 3, and 4. And we have the for alphabet A comma B with the length n, the number of strings can be generated equal to 2 power n. So 2 is the input value and n is an n number of length. N gives the length. So here we have the string. Four strings are going to be provided. So 2 power n. Next one we have the concept is closure representation. In this closure representation, we have the two types. One is the positive closure, another one is the clean closure. So positive closure is represented as L plus. L plus means what here? The set of all the strings except null value. That means all other positive values. There is no null value. So if we consider that string sigma equal to a comma b, it will starts with a, b, a b, b a like that. But here we are not having the epsilon. Empty value is not included in the positive closure. While coming to the clean closure, it will be represented as L star. L star means here epsilon dot L plus. So epsilon is going to be included in the enclosure with the positive closure. Coming to the example here, we have that we are consider the regular expression for a language accepted all the combinations of m's over sigma equal to m. The input value is m here considered. So R is regular expression equal to m plus. M plus means it is an positive closure. So the set will becomes like this: R equal to m comma mm, mmm, 4m's, 5m's, and so on. So the first letter is m. So here we are not considering the epsilon. So the set will becomes the m square, m cube, m power 4, m power 5 like that up to and so on, m power n. Next, R equal to M star. M star indicates this clean closure. So here the R equal to epsilon, m square, m cube, m power 4 like that. We are getting the different set of values with the combination of m. If we take in that set equal to a comma b with another input values or m comma n, then we will get the mn like that with the combination of n also. Let's come into the input. Another string we considered, that is a God God. Here we consider that summation star, that is a clean closure. Here we include in that epsilon comma. Last string is God. So G can be repeated any times. In the same way, D can be repeated, O can be repeated. So like that, we can get the any number of combinations with the string God. Let's come into language. Language is represented as language L. L is a set of language is a set of strings chosen from the some sigma star. So, or we can say that a language is a subset of sigma star. So we are going to consider a subset. There is a we have the string in that string we are going to consider the substring. It's called a subset. A language can be formed over the sigma. From where we are getting means from the input values only we are getting the language. Can be finite or a infinite value. Example of a finite language. Here we consider that L1 equal to set of string of 2, length 2. That is L1 equal to, we consider that input strings are x comma y. So length 2 means x comma y we consider it. So based on that we get in the combinations xy, yz, sorry, xy, yx, xx, yy like that we get in the combinations. For the infinite, all the strings started with the b. That means we consider that condition, that is the string will be start with the B. So first letter should be the B. Must and should it will start with the B. So L1 equal to B A B B B A A B A B B B B A A, B, and so on. Like that, we can consider any number of strings. Must it should be start with a B. That is about the language. So, so this gives the finite language. So this is about the computation theory of computation basic what we are going to be used to implement the theory of computation, the notations, and what the language we are going to be used in this as we seen here. In next class, we will see the what the next topic.